Hello, everyone. This is our final presentation for CSCE 440 numerical analysis class at UL for fall of 2021. I'm Tate Anderson, and I'm here with Brandon Ramos and Ivan Cheah. So today, just for an overview, we're going to be we're going to go through our motivation and our goals for this project. We're going to be looking at our data source. We're going to be going over the numerical analysis methods that we used, the implementation of those, and the results of those methods. And then finally, we're going to go into our conclusions and future work. So looking at our motivations and goals for this project, we looked at the housing of universities for this project, and the reason for doing that is that housing management for universities is a really big part of universities, and the management can cause many issues if not done properly. And also just the number of students living in university housing can change drastically every year. So it's important to look at those trends and for universities to find how they can best manage housing options. So universities need to be prepared to have enough housing for all students without overspending resources on housing that will go unused. They need to manage it in the right way so that they have enough housing, but that they're not going overboard. And so in this project, we're going to be employing numerical analysis methods on UNL's student housing numbers. And by doing that, we want to be able to examine trends in the housing numbers and attempt to provide an insight on housing growth.
So the data sources that we used for our project came from UNL's websites during this Common Data Set initiative that was started in 2000, and it goes all the way from the academic year in 2019. So there is 20 different papers to look through. And looking at one of those, we're mainly focusing on section B and F, which section B tells us the enrollment and persistence rate for each year, and section B, it has the grand total of students for the year. And then in section F for student life, we mainly look at the percentage of undergrads who lived in the college-owned, operated, or affiliated housing. So from there, we look into the numerical analysis methods. So the first one that we're going to look at will be the R-cubic spline interpolation. And then next, we will talk about the piecewise linear approximation, and we'll end off with the least squares approximation. So looking at the implementation of the R-cubic spline, we basically have a couple of matrices, such as the B matrix, which can be seen on the right, where we assume our H is 1, and we have a R value, which is expressed in the top right. From there, we also have an alpha, a C, a B, and a D matrix, where our A matrix seen in the equation below is given by the data points. From these equations up top, you can actually obtain the equations for the interpolated values, or the interpolated functions from S naught all the way up to S n minus 1, where n is the total number of data points. And next, as we can see here, we have 20 different data points, and our A values are basically just the data points for that year. So as you can see, in 2000, we had 5,400 students present in the dorms. On the right, we can also see the MATLAB code for calculating those matrices, and then we have a simple for loop just to print off each one of those equations that we generated before. So the results of the R-cubic spline method are shown here in the figure, ranging from 2000 to actually 2001 to 2020, where we have both R-cubic and the linear line, where we can see that we have sometimes a big difference, which can be seen from 2004 to 2005, but we do have a pretty good fit line for 2005 and 2006.
So next up, we're going to be looking at the second method that was implemented, which was piecewise linear approximation. So just doing a brief overview of how this method works. Looking at that figure on the left, piecewise linear approximation, as it implies, is going to be constructing a piecewise linear function, and it's going to do that by looking at a certain error tolerance that is provided by the user. And while the method does not guarantee that the lines that are created will cross through the actual data point given by P1 on that figure on the left, while it does not guarantee that it will cross through that, it will be within plus or minus that certain error tolerance, as you can see in that figure on the left. And on the right kind of shows how those slopes are compared. We'll get into that in the next slide, but this figure on the right shows how those lines are created in comparison to the original points. And again, we compare those slopes to choose which line we're going to add to the function. And so here we have the pseudocode that was given in the slides for this class, and also the MATLAB code that was implemented. And as we can see in the pseudocode on the left, what this is doing is it's looping through, it's comparing the slope to the previous slope that we're given, basically, plus or minus the error tolerance, assigning a new value, and then comparing those two. And by going through that, when we compare, we decide which one's greater than the other, SL prime or SU prime. And then from there, depending on how that, depending on the result of that, we can add that line to the function, which is what we see there. And again, on the right is just the MATLAB implementation of that. Pretty straightforward, just a bunch of computations going on there and adding those lines to the MATLAB array. And so here we have the results for the implementation of the piecewise linear approximation in MATLAB. I ran this with 3 different error values. On the left, we have an error tolerance of 50, in the middle 200, and on the right of 500. And again, what that means is, given that error value, the approximated line is always going to be within that much of the original value. So again, 50, 200, and 500. And as we can see, the smaller the error, the more pieces that will be generated, and therefore the closer fit to the original data. So on the left, with an error tolerance of 50, we get 17 pieces, and it's a very close fit to those original values. In the middle, if we bump it up to 200, that puts us down to 12 pieces. And it's still a decent fit, but you can see it, because it has less pieces, it does not line up as well as a lower error tolerance. And then finally, on the right, we have the 500 error tolerance, and that one with only 6 pieces is quite off, quite far away from a lot of those points, just because there are fewer pieces to do. But the advantage of a higher error tolerance is a lower execution time. As you can see, it's nearly a third of the execution time at 500 is nearly a third of what it is at 50. And in addition, we can look at the root mean square error, which goes up as we increase the error tolerance. And then looking a little more in depth at that calculated error, on the left, we have the actual value of the undergrads on campus every year, and the years corresponding with that. And then for each error that was calculated, 50, 200, and 500, we have the values of the approximated lines for each of those years. And then at the bottom of those columns, we have the calculated root mean square error for each of those tolerance values.
Hello, I'm Ivan, and I implemented the linear least squares approximations method for our data, which gives us a y equals mx plus b best fit. From the formulas on the left, it's pretty easy to implement MATLAB. So we just take the sum of the X and Y columns respectively to find our A1 and A0 values. A1 being the slope value and A0 being the y-intercept. On the right is the implementation in MATLAB. And here are the graphs and their respective fit functions. The total number of students on campus over the course of 20 years on the left, and the total percentage of students on in-campus housing over the course of 20 years on the right side. The blue line plotted is our plotted data, and the red line is our best fit line. From these figures, we can see that the linear least squares approximation is good for getting us a rough trend line. We can see it's obviously increasing, but not very good for getting us accurate values. If we were to enter in a t value into the function, as the best fit line hardly ever intercepts with the actual data. In conclusion, we recommend piecewise linear approximation because it best fits the plotted data with a small enough root mean square error. The more pieces there are, although the runtime grows, the more pieces there are. This is an okay trade-off considering how well it fits. Because students don't usually drop out of or cancel a housing plan mid-semester, we don't think that it matters that the data is not a smooth curve. For our future work, we plan to be able to predict admission trends for schools using more complicated software. One thing that I thought of was using machine learning, which takes advantage of root mean square error analysis, and also to take into account more variables like admission rates. We also want to take a deeper look into factors that affect the yearly admission rates and the choice to live on campus. One example would be like economic shifts or the kind of growth of yearly earnings. We also want to be able to compare the errors of our implementations. Thank you.
One of the questions that we got when presenting this work to our classmates was basically looking at the on-campus student housing between 2005 and 2007. What the question was, what did we assume that would happen? What did we assume happened between those 2 years for the nearly double increase of having students on campus? And we think the reason for that was sometime around 2005, there was a some sort of agreement with the university that for either freshman or first year students at UNL had to live up on campus. And this was more or less for having the dropout rates be minimized.